today's lecture we will be moving on from lattices to a special class of lattices called Boolean algebra. Now, as we have already seen that a lattice is a partially ordered set written as poset with the property that any two elements in it has a greatest lower bound and a least upper bound. So, we can rephrase whatever we have said now as suppose L is a lattice with a partial order denoted by the symbol less or equal, then for any two elements A B inside L, we can define an element called the greatest lower bound of A B, in short GLB of A B, greatest lower bound of A B, which we are writing as GLB of A B, and least upper bound of A B. We can as well write it as a set A B, that is L U B of A B. Now, what the definition of a lattice tells us is that in a lattice any two elements will have a greatest lower bound and a least upper bound. Because of this, we can in fact write this GLB and LUB as binary operations over L. We will denote them by symbols like V and wedge. So, GLB of A B is denoted by A and a wedge then B. We will also sometimes denote it just by A dot B, and LUB, that is the least upper bound of A B, is denoted by A V B. We sometimes will be denoting by A plus B. Now, this A dot B or this A wedge B is called conjunction, or the meet operation, and A V B or A plus B is called disjunction, or the join operation. Now, in this lecture we will be using plus and dot instead of the V and wedge. Now, there are certain properties of this meet and join that we will discuss now. One is idempotent, or idempotency property. This states that A plus A equal to A and A dot A is equal to A. Now, this does not come as a surprise to us, because we know that when we take the plus operation, it is essentially the least upper bound of the elements. Now, if my set is singleton, so I have got A and A, so the least upper bound is A itself, and similarly for greatest lower bound. The next property that we discuss is commutativity. If we have two elements A and B inside L, then A plus B is equal to B plus A and A dot B equal to B dot A. This is also somewhat easy to think of, because A plus B is nothing but the least upper bound of the set A B, and as we know, the elements of a set are not ordered. So, least upper bound of A B is same as the least upper bound of B A. Similarly, A dot B is the greatest lower bound of the set A B, which is same as the greatest lower bound of the set B A. So, these two, the first two properties of this GLB and LUB operations need no proof as such. Now, we come to another property which is called absorption. Now, this absorption property needs a proof. Well, we are starting with two elements A and B, and we see that A dot B is definitely something which is less or equal A. The reason is that A dot B is the greatest lower bound of A and B, then of course, A will dominate A dot B, and therefore, if we consider the least upper bound of the set A and A dot B, right. So, if we consider the least upper bound L U B, this is nothing but A plus A dot B, this of course will give me A. Therefore, I get the first absorption rule, and then in the next case we note that A plus B is definitely dominating A. The reason is that if you consider A plus B, it is the least upper bound of A and B, therefore, A will be less or equal to A plus B, but then if we compare A and A plus B, then the greatest lower bound of the set A and A plus B is going to be A. In other words, A dot A plus B is going to be A. So, these are the first two absorption laws over here, and next we move on to associativity. Which states that A plus B plus C is equal to A plus B plus C, and A dot B dot C is equal to A dot B dot C. Now, in a lattice, even these rules need a proof. I will give the proof of the first associativity law and then leave the other part for exercise. Now, let us look at the rule again. We want to show that A plus B plus C equal to A plus B plus C. In order to do that, we first start by checking A. A is definitely less or equal to A plus B, and A plus B is definitely less or equal to A plus B plus C. Well, the reason is that A plus B is the least upper bound of A and B, therefore, it must dominate A, and A plus B plus C that I write here is the least upper bound of A plus B and C, therefore, it must dominate A plus B. So, by using the transitive law now, because we know that after all we are looking at partial order relations, using transitivity of the partial order, we have A less or equal A plus B plus C. Now, let us look at B and C. Now, let us put this first in a box and then start off with B. Now, B is definitely less or equal A plus B, and A plus B is less or equal A plus B plus C. Therefore, we can write again by using transitivity of the partial order involved, B less or equal A plus B plus C. We again put it in a box. The next candidate is C. Start with C, and of course, C is less or equal A plus B plus C. We put it in a box. Now, we would like to combine these two results. If you look at this, we will see that in the both two boxes, the right hand side is same, that is A plus B within bracket plus C, and B is less than A plus B plus C. C is also less or equal A plus B plus C. Now, We know that we are working in a lattice, therefore, B and C will have a least upper bound. Definitely A plus B plus C is an upper bound for the set B C. We write it down, A plus B plus C is an upper bound for the set B C. Therefore, any least upper bound will be dominated by this upper bound. So, we know that the existence of the least upper bound of B and C is guaranteed. So, which we denote by B plus C. Therefore, B plus C will be less or equal A plus B plus C. Why? The reason is that since B plus C is the least upper bound of the set containing B C. Now, we put a bracket over here as well. Now, we see this and this. Again we see that A plus B plus C dominates A, that is A is related to A plus B plus C, it is less or equal A plus B plus C, whatever we may say, remembering that it is a lattice, and B plus C is also less or equal A plus B plus C. Now, of course, we can take the least upper bound of A and B plus C, which is A plus B plus C, and this will be less than a general upper bound, any general upper bound, and one of them is A plus B plus C. Thus, we see that we have been able to prove that A plus B plus C is related to A plus B plus C or less or equal A plus B plus C, as we choose to say in a lattice. Now, what about the other way round? Now, if we look at this last relation, we will see that in the bracket in the left hand side we have B C, and in the right hand side we have A B, and outside we have A and C, that is the remaining symbol. So, this gives an idea. What about if we exchange A and C, that is exchange A and C, where let us call it equation 1, or it is not an equation, it is call it the relation 1 in 1. If we do that, we will get C plus B plus A is less or equal C plus B plus A, rearranging the terms using commutativity, and we need only commutativity. We will get A plus B plus C. So, I am using commutativity here, and commutativity here is less or equal, again using commutativity, A plus B plus C. So, let us call it 2. So, we have got now 2 and we have got 1. We remember that after all we are working in a lattice. So, therefore, it is antisymmetric, So, these two relations together imply that A plus B plus C is equal to A plus B plus C. Thus, we have proved just now that in a lattice associativity holds for addition, and what I leave as exercise is the meet operation or product, whatever you say, to prove that A dot B dot C equal to A dot B dot C. What I can tell you is that it is almost the same. The underlying ideas are more or less same. Now, we make a statement that we do not prove explicitly, but it is more or less clear. We are considering finite lattices. We state that in a finite lattice there exists a unique least element and a unique greatest element. The question is why? The reason is that given any two elements, I can find a least element, and if I just pick up all the elements and mutually take least element and the least element of the least element, ultimately I will arrive at the least. So, let me reword it. Given any two elements, I get a least upper greatest lower bound. So, if I keep on doing that for all the elements and then construct all the greatest lower bounds and then do the same thing for all the greatest lower bounds. So, ultimately I will arrive at one element which is the least element in the whole lattice. The reason is that we do not have infinitely many elements. So, whichever chain, by using whichever chain we go downward, we will stop at one element, and which is going to work as the least element of the whole lattice. And similarly, we have the idea of least upper bound. So, we go on like that and get a greatest element. This unique least element is denoted usually by the symbol 0. This unique least element is denoted by the symbol 0 and the greatest element by the symbol 1, and given any element A in the lattice L, we have the properties A plus 0 is equal to A and A dot 1 is A dot 0 is 0 and A plus 1 is 1. So, these are the things which are again more or less straightforward, because after all 0 is the greatest element. So, if I take the least upper bound of A and 0, it is 0 is the least element. So, if I and so whatever element I take A, it is going to dominate 0. Therefore, if I take the least upper bound, it is going to be A, and 1 is the greatest element. Therefore, if I take the lower bound of 1 and A, for any A, it is going to be A. Similarly, the other two cases. Now, we come to the question of distributivity in a lattice. Now, a lattice is called a distributive lattice if for any A, B, C in that lattice, and I must mention here that A, B, C's need not be distinct. We must have A plus B dot C equal to A plus B dot A plus C and A dot B plus C equal to A dot B plus A dot C. Now, the next natural question that comes here is that is any lattice distributive, and the answer is no. There are lattices which are not distributive. I will give examples of two lattices which are not distributive. So, first one is like this. So, suppose this is A, this is B, this is C, this is C, so this is C, this is D and this is E, and I connect them and this gives me a Hasse diagram. Now, let us consider the product B well, I am using the other notation. So, I change my notation. Let us consider B plus C, all right. Now, let us evaluate C dot D is C and D, this is A, and B plus A gives me B. So, I can write that B plus C D is B. All right. If we consider B plus C and B plus D, this will mean B plus C is E and B plus D is E. Therefore, E meet E gives me E. We put this in a box. Comparing these two, we see that of course, B is not E. Therefore, in this case B plus C D is not equal to B plus C meet B plus D. So, this lattice is not distributive. Next, we check another lattice which is not distributive, which is given by a Hasse diagram like this. We have now 5 elements. We have got A over here, then B, then D, and at the top, well, let me write E here because I will put C over here. Now, let us see whether we can find out some combinations where which will not be distributive. So, let us start from here D, and then let us consider D plus B E. Now, this is D plus, this is not E, this is C. So, this is C, D plus B C. Now, B C is A. So, D plus A. So, this gives me D. On the other hand, D plus B gives me D, and D plus C gives me E, and if I take a product, D plus B product D plus C, well, this I see that this does not work out, I get again D. So, it does not work out. So, we need some other combination. Let us try something else. Let us try the other way. So, let us consider D dot B plus C, which is D meet B plus C is E. This gives me D, and D meet B plus D meet C. D meet B will definitely give me B, and D meet C gives me A. So, this gives me B. All right. So, here we see that for this particular case this does not work out, but if we change the plus with dot and dot with plus, when we see that we have a situation here where of course B is not equal to D, therefore, we have D B plus C equal to D B plus D C. They are not equal. Thus, we see that this lattice as well as the one we discussed previous to this, both are non-distributive. So, these are examples of non-distributive lattices. However, for our purpose we will be considering only distributive lattices, and not only that, distributive lattices which has complements. So, we define another operation on a lattice which has got a greatest element and a least element. So, I am considering a lattice L with a partial order which is distributive, has greatest and least elements, denoted by 1 and 0 respectively, we are considering this, and we define a unary operation on it which is called complement. For any element A belonging to L, the complement of A in L is an element A prime. We will be writing this as a prime of the original element, such that A plus A prime is equal to 1 and A dot A prime is equal to 0. if a lattice has a if a lattice is such that any element of it has a complement, then it is called a complemented lattice. We have to note here is that this complementation is not restricted to the distributive lattices. We can have complemented lattices which are not distributive. In fact, a closer analysis will show us that the two non-distributive lattices that we constructed just before are complemented lattices, but now we are not considering that. We are considering distributive lattices having greatest and least elements and which are complemented, which is a complemented lattice as well, and these lattices are called Boolean algebras. So, I am now in a position to define a Boolean algebra Boolean algebra is a complemented distributive lattice with the operations plus, dot and complementation defined as above. So, here in all these contexts we must remember that we are not only looking at a set, we have a set, but on that set there are operations, there are elements and all that, and together it is forming an algebra. So, suppose I have a set B. On this set B we define a partial order. Suppose with respect to that partial order it becomes a lattice, and because it becomes a lattice we have two operations defined on it, that is plus and dot, which is the least upper bound and greatest lower bound, and then suppose the greatest element and least element exist and we can define a complement operation, which is a unary operation, and suppose it is a complemented lattice with respect to this complementation, and that complemented lattice is a distributive lattice. We have discussed the distributive law. So, we put all these operations together with the symbols for the greatest element and least element, and what we get is called a Boolean algebra, and we can denote it by a script B. Now, the question is what is the simplest possible Boolean algebra, and we indeed know probably the simplest possible algebraic structure that can ever be, and that is a Boolean algebra that contains only 2 elements. Here please note that if we have just a set with 1 element, we can have nothing. So, we have a set with 2 elements, let us call them 0 and 1, call this set B, and define plus as this 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 1, and let us define dot in this way 0 1 0 1 0 0 0 1 is 0, 1 0 is 0, and 1 1 is 1, and let us define complement the unary operation in this way, that 0 is changed to 1 and 1 is changed to 0, and what we have is a Boolean algebra, and this is denoted by we can denote it by 0 1, which we are then plus dot this complement 0 1. So, this all together gives me B. Now, if we want to generate more Boolean algebras, the best way is to take Cartesian product of this B. So, for example, we can take B2, which is the Cartesian product of B and B, then we get this set, well 0 0 0 1 1 0 1 1 plus dot complement, and the least element is 0 0, greatest element is 1 1. Now, one can ask a question over here, that what do I mean by this plus, and what do I mean by this dot and the complement operation. Here we note that if we consider just the set, let us say B, which is essentially 0 0 0 1 1 1 1 0 and 1 1, any two general elements of B can be written as x 1 x 2 and y 1 y 2, both belonging to B. Then x 1 comma x 2 y 1 comma y 2 belongs to, I am sorry, I change it, this is B square, this is B cross B, this is B cross B. So, here it is B square, but this x 1 x 2 y 1 y 2 are in B. So, x 1 x 2 will behave as elements in B. Therefore, we can define the plus and dot by using the operations on B, that is x 1 x 2 plus y1 y2 will be x1 plus x2 y1 plus y2. No, this is not correct. So, I will change it. This will be x1 plus y1 x2 plus y2. Now, we do not have to worry about this plus is already defined over here, and this is the plus that we are defining on B cross B by using the addition that we have already defined. Similarly, we can define x1 comma x2 meet y1 y2 as x1 y1 dot here x2 dot y2, and we again remember that this meet or dot or product, whatever we say, is same as this one, and we can check that the operations defined in this way follow the rules of a Boolean algebra. And for the complement, again if we have x1 x2 complement, we will just define it as x1 complement x2 complement. Thus, we see that given our very small and simple Boolean algebra, we can take on take Cartesian products of this and generate new Boolean algebras, and we will see later on that any finite Boolean algebra is essentially Cartesian products of B with respect to the operations that I have just now described for B2. So, for today we shall stop. In the next lecture we will continue our discussions on Boolean algebras and functions on Boolean algebras. Thank you.